Welcome everyone to How to Engineer a System of Systems Using Core, presented by Fran McCafferty, pardon me. My name is Donna Long and I will be your host during today's webinar. Fran McCafferty is a practicing principal systems engineer leveraging experience gained over a 30-year career. Fran was one of the early pioneers in applying model-based systems engineering, serving as the GE-era Strategic Defense Initiative Requirements Manager. He has also led numerous project architecture development efforts for commercial, U.S., and foreign defense projects. Before Fran gets started, I have a few housekeeping items. We will be answering questions at the end of the webinar. Please send your questions in as soon as you think of them through the question tab on the webinar control panel. Fran will answer as many questions as he can today, but if we do not get to your question, we will reach out to you after the webinar. The webinar is being recorded. If you experience connection problems during the live presentation, a recording will be available within 1 business day. The recording will be published to Vitek's webinar archive located on our website. At the conclusion of this webinar, a survey will open on your screen. Please take a moment to give us feedback on today's presentation or on what topics you would like to see covered in future webinars. Now I'm going to turn the presentation over to Fran. Welcome, and thank you for joining us.
Good morning, everyone. I'm Fran McCafferty. I'm a principal system engineer with Vitek Corporation. Just to give you a little bit more, Donna gave you a brief introduction. I've been in R&D design projects for the past 30 years. Most recently, I was part of the Electronics Manufacturing Productivity Facility. It's a Navy Center of Excellence with a focus on advanced microelectronics design and how we can install innovation throughout the Navy's electronics views. Also, just as a reference point, I was the technical director for the U.S. Coast Guard program known as Deepwater. It was a recapitalization of the U.S. Coast Guard assets. And Donna brought up the first thing is I cut my teeth with the SDI program as the requirements manager. I worked for GE Aerospace, and we use model-based system engineering pretty extensively, developing the different paradigms, implementing the best practices that were available at that day. And that goes back into the 1980s. Okay, so the first thing I'd like to do is I'd like to try to level set where everybody's expectations are. The screen has quite a few words on it, but what I wanted to try to emphasize is that Vitek is a system engineering company. We have 3 focus areas that we spend the majority of our efforts on. The first is the practice and knowledge leadership of system engineering. Throughout the industry, we're constantly interviewing and understanding what the best practices are, and we incorporate those things. We also evangelize system engineering throughout the community. Our president of the corporation is David Long. He's a past president of Incosi. And then the third element that Vitek focuses on is automation, model-based system engineering tools. We have 2 product lines, Core and Genesis, that implement all the methodologies that we discussed throughout our innovation of system engineering. So going back to what's on the slide physically, Mike Ryan is an industry-recognized system engineering leader. And what we're trying to do is say, not only does Mike Ryan have a methodology, not only does Vitek have a methodology, but they're both aligned. We're implementing industry standards. So I wanted to go through and say, it's not just us saying this is the difference between a system of systems or a system of subsystems. It's also recognized throughout the industry what is involved. On the next slide, I'm trying to graphically depict what the differences are. On the left-hand side, it's a graphic that's an OV1 of the Deepwater program. I told you I was the technical director of. If you look at all the different components, the different elements, different concepts of Deepwater, there was a combination of air assets, fixed wing, rotary wing. There was also the ship base. There were small boats, smaller cutters, larger cutters, and then there were ground stations. And all of those things had to work together in order for the Coast Guard to meet its missions. But on an individual basis, the system of systems, each cutter was highly capable of performing a lot of different things. It was tuned to be ideal for its particular environment. But it also had to have the reference that it could satisfy the missions that the Coast Guard wanted to have. So the point on here is that each of the subsystems were standalone systems unto themselves. They could be repurposed, reused for whatever else it was necessary to be used for. On the right-hand side, what I'm depicting is a radar system that the Navy is currently fielding. It's operational on some of the large decks and even some of the medium decks. It's actually on one of the Coast Guard cutters as well. It's the Spook 9B radar. It's a dual-mode radar. It does air search and surface search. Now, the reason I'm pointing that out is this will be part of our example moving forward. The concept underneath it is that the Spook 9B radar has multiple subsystems unto itself. What we're depicting on the graphic is the top is the antenna, the left is the transmitter, middle receiver, and the right-hand side is the signal processing unit. These were not designed independently. They were designed as a concerted whole so that the Spook 9B could do its dual-mode radar mission. So the point, the takeaway is that each of the subsystems was focused, tweaked, adjusted, modified so that it would work together to give the overall system performance optimization versus what the individual subsystems were. So I wanted to show you what those things were first. And we're going to go into what the Spook 9B is. That'll be the focus of our discussions moving forward. Sorry to give you a lot of the early dissertation, but I think it's important that we're on the same page to move out, that we understand the concepts and talk the same language. The point that I'm trying to make with this slide is that you have a consolidated hierarchy of different concepts that are being presented in a design. And it depends on where you're starting from, what you consider to be a system or a subsystem or a system of systems for that matter. And what we're going to show you is that the concept of a system of systems doesn't only apply to enormous systems like the Coast Guard, Deepwater. It also applies to other things. It applies to things like the Spook 9B radar. What you see is that generally, and almost throughout, you're going to see that a system has to do something. It's the classical IPO, input, process, output. Something stimulates a system, it does something, and it produces some level of output. And the things interconnect, they work together in order to support their overall missions. The subsystem, it really depends on where you're looking. If you go back to our old days of the SSS, a system segment spec, that spec could be either focused at either layer, at the system or something lower on, but it followed the A spec format. It used to be 490A, I think is what it was referred to as. So we're looking at how we break these things down. Now, when we look at the system of systems, one of the fundamental reasons that it varies is that we don't always have one large contractor doing all the work. Very often, we have multiple companies, maybe multiple geographies within one company, but it's not specifically on one campus where engineering is on the left-hand side of the campus, and they can run over to support the manufacturing, which is located on the right. So there's going to be fundamental differences and segregations that have to take place in order for the system to work. And it doesn't happen just by chance that we go to integration and test and it's all going to work together. If we don't focus on how these things are going to be partitioned and then how they're going to come back together from the very inception, your probability of success goes down significantly. So when we look at it, we've got a large system, multiple contributors, multiple geographies, multiple design teams with different cultures. If we have a multi-contractor base, the way business is performed is probably going to be significantly different. So we have to establish the rules of how these systems are going to inter-cooperate. And I think the same thing applies for large single systems. What was it designed for? What were the prioritizations that its stakeholders had? Was it based on functionality? Did they have to reuse a specific piece of equipment that was throughout the fielding exercise? What was the expertise level? Because very often people bring to a project what they know. They're not necessarily going to look for some new and innovative answer. They're going to bring to you things they know are successful because of their past experience. And they all have to be factored in. And we also have to protect against those same things in order for a system to behave properly. So we're going to go back to our radar restoration. The Spook 9B was conceived in the late 80s and early 90s and went into production during the 90s. So the system's been fielded, and it's very successful. It does what it's supposed to do, and it does it quite well. The Spook 9B has a high-power amplifier system that's tube-based. You think, well, that's okay. Why isn't it solid state? Well, when it was being developed to get to the high power levels, the tube-based product base was what had to take place. Well, I don't know how many people recall, but not in the not too distant past, there's been a major push to go to higher energy efficient light bulbs. We've gone from incandescent light bulbs, and now we're at LEDs. Well, one of the unintended consequences that took place was that the tube manufacturers are starting to go away. And the ability for the Navy to get tube-based amplifiers is becoming much more critical, very costly, and difficult to sustain. The anticipation is that this radar is going to be in play for probably another 20 years. So the Navy's really concerned about how it's going to support this mission-critical system. So what we're looking at is what are ways that we can go through and protect the mission of this system, but also be able to consistently put new technologies in, address new missions as they arise, and have the system sustainable throughout that next 20 years. So there's some questions that we might want to ask. What are the options? So I've made a claim that the tubes are becoming more and more difficult to support and service. Well, we could just throw away the whole radar. But you're going to run into some issues whenever you have that kind of concept because the investment that's already made. And it's not always the design, it's not always the manufacturing. It's often how this piece of equipment or this system of systems interacts with a larger segment of system of systems. And it's not just trivially replace one piece of gear with another because of that proof that it's not going to cause detrimental effects on the rest of the system. On the other side, if we're going to try to maintain the Spook 9B for 20 years, is that going to be a real problem? What's the source of supply situation? Will we be able to support this equipment for 20 years? Will the parts be available as the system needs to be upgraded, refreshed, maintained, and supported? So what I wanted to do is just go through the listings of some of the options that an engineer or system engineer has to go through. So the options, could we replace the entire system? Sure. There's constantly going to be new and better systems that are fielded throughout industry or even development items. Can we go off and do a design from scratch? Probably yes, but the impacts are it's going to have a significant cost. It may be multiple, maybe a decade, years before the system goes from inception through fielding. And then you have the integration challenges. How do we get that system to work with all the other legacy contributing systems on board a platform like a DDG or a large deck amphib? Could we go off and use a system that's on another platform? Well, it's the same thing. Do you still have cost integration, and does it have the capability? When a system's already built, it's probably been designed to meet its specific requirements, the capabilities that it had to do. It may not meet the mission requirements that our specific implementation has to do, so that has to be considered. Now we have the maintain. The reference that the tubes break regularly, and there's a high cost of maintaining those things. Can we still get them? That's always going to be a challenge. So we're going to look at things like form-fit functional replacements. What's available? How can we use them? What are the modifications? What are our contexts available to us? So now we look at, can we also perform capability upgrades? There's a concept I've been hearing more and more about throughout the industry, and it's a mission-based engineering. And what my interpretation of that is, we know what our enemies do today, but will we know what they do tomorrow? And how do we future-proof ourselves so that when these things take place, we can protect ourselves? So the graphic on the right was done by a world-famous artist called Frans. That's me. And what my point on here is that we need to be able to evolve. It's not enough that we meet our mission and our capabilities of today, but we've got to be able to figure out how we can make it that as new things evolve, new technologies come out of the semiconductor environment, new software applications, how can we take full advantage of those things without blowing up our entire system and saying we've got to start from scratch? My point being is you can't do that unless you figure out how to put those technologies in. You have to have an open enough architecture that it will support what you're trying to do. It won't happen by happenstance. It's got to be premeditated in order for it to work. Because we can't afford to be stagnant. We can't afford to stay still while the rest of the world evolves. The point I'd like to make on this slide is this is kind of the focus of how the overall Spook 9B world's coming together. It has its major subsystems. They're called out. They were optimized because the system met its requirements. And one of the challenges that you run into is that when one large contract is let, there's not necessarily the separation of concerns. The receiver doesn't necessarily stand alone from the transmitter or from the antenna. Very often, because it was convenient or there was some design attribute that made us put equipment in one place or another, that when we would try to do a segregation between a transmitter and a receiver, there's equipment, there's functionality that can't be separated. It makes it very, very difficult for that system to be maintained throughout the life cycle. So moving forward, when we're trying to look at how is the system going to come apart and go back together, we're going to have to be able to clearly identify the bright boundaries between things like the transmitter or the antenna. We'll be able to offer a complete replacement of that subsystem without affecting all the downstream elements. And that may be that we're going to have multiple contractors throughout different geographies. We may want to partition it based on functionality. We may have source matter expert organizations that have gee whiz great technology that we want to be able to put in, but we're going to have to be able to segregate these things in order to get them to play together. What I'm showing you on this slide is realistically nothing new. It's the classical system engineering V diagram, and it's turned on its side to show time sequence for the schedule. The elements on the left-hand side represent where we start. If you look at where things are in a system, use the Spook 9B as an example, we need to fully understand all the aspects of that system as it is today. Know what the physical hardwares are, what is the behavior, which is a combination of functionality, information, and control flows. We're going to need to know what its performance is. So we're going to have to go through and build models up so that we do no harm. We can do exactly what the old system did, and with the intention that it's going to be better, faster, cheaper, cooler, niftier, neato. After we define all those things, then we can go off and decide how we're going to partition it. How can we get from where we were in the baseline system, the gray boxes, over to the right-hand side where we have the new capability, the new equipment, the new supportability structures that are involved. So what do we do? In our methodology inside of the paradigm, what we really want to focus in on is how do we clearly define what the boundaries are. So using the Spook 9B as an example, we define how it interacts with the outside world, the environments, the targets that it's going to track, and then also how it's going to interact with the combat system, how it's going to interact with the weapon systems. Because this thing is a critical system for self-protection on a ship. It has to be able to detect early, provide the information over to the command and control so that targeting solutions can be developed, and that it can also take out the hostile elements. We can't sacrifice that. We need to know how it works today, because one of the estimates is that it may be tens of millions of dollars to develop a radar, but it could be hundreds of millions of dollars to integrate that system throughout the entire platform, the cruiser, destroyer, or amphib. So there's a real serious consideration of how does that work. We don't have the luxury of going off and changing the legacy systems. We're focused in on the radar. So the radar has to faithfully represent. But on the other side of it is we also have to perform the balance of how do we get new technologies into it. So we need to know what the system boundaries are. We need to know what its size, weight, power, plus costs are. We need to know what the interfaces are. How does it interface to the outside world? And as we develop down lower details, we need to understand how does an individual subsystem react with another subsystem and flow that throughout. So the interface definition is absolutely critical to understand the system boundary as well as the subsystem boundary. Understanding what the physical characteristics are allow us to replace racks of equipment below decks with future equipment. And we're probably going to get more capability in the same footprint because of miniaturization. Managing the complexity, if you don't model an overall system, it becomes rather cumbersome in order to understand what the impact of a change is. Our recommendation is you want to system engineer your design elements. We want to system engineer the Spook 9B. We're going to model it. We're going to put it into our Vitek's core product, and by doing that, we're going to understand what the original requirements are. As we modify the requirements or modify the missions which drive requirements, we'll be able to see how those things flow throughout, and we can give a very clear impact analysis of how the system is going to evolve to meet the new mission, meet the new requirements. We need to know, that's the key for system engineering, is we need to know how the system works and how we intend for it to work. Reverse engineering the system. What we're going to look at is how do we gather all the relative and relevant information. What are the specifications, what are the CON-ups, what are the ICDs, how are all those things documented today? One of the problems that the Navy runs into is that on a large contract, the level of design detail isn't realistically available to them, that they can go through and peel down and fully understand the complexity of a potential change. We often refer to the $1 million requirement. The $1 million requirement isn't necessarily to perform that particular capability, but it's how it affects all the other downstream elements of your system, the interfaces, the receiving functionality. So what we're going to recommend is that you capture all that information inside of, for instance, Vitek's core. We want to model the physical architecture. My thought process goes through, we clearly identify inside of a spec what the system elements are, what the subsystem elements are. You could drive it down to many layers and particularly have an integrated bill of materials if you were so inclined. One of the challenges is where do you define the lowest level? Where is it that you're going to discuss the acquisition? And we'll get to that in a moment. We also think that you need to understand behavior. And when I throw out the term behavior, not everybody always understands it. If you're a model-based system engineering person, it's first nature. If you're new to it, we want to take a second. So behavior is a representation of the functionality of a system. It's defining what does it have to do. What information is traversing the system boundary, maybe feeding one function from another function. So it's the triggering events that authorize a function to execute, or it might be a data store where there's some semi-static information available for a lookup. But there's also the control. What causes one function to execute? Which order are they going to execute in? And is there any criticality timing requirements to it? Because it's not enough for a function to execute. It needs to execute inside of the time budgets in order to meet the overall mission. If you were looking at a missile, within 3 seconds, there's a lot that changes, and we may lose track if we take too long to go through it. So we need to understand what our time budgets are. The interfaces, once again, what wires are connecting where, what information is going to traverse those things, and then what is the size, weight, power. Oftentimes what we're looking at is we only have a prescribed budget of space that's available. We only have so much power. We only have so much HVAC to cool the equipment. So we need to understand what those things are. We often don't worry about those as being as critical as, say, being able to have an accuracy of the track to within a meter. We often put a lot of emphasis on that accuracy, and we forget about we need to have enough power to energize all of our circuitry. In our model, all of those things are integrated together because a function gets allocated to an architecture that has components. The components interact with each other over a logical interface, and inside of that we're defining what the links are between one component and another, and we associate the constraints to the physical entities so we know how much power it is. We can do our analysis top to bottom to find out, are we inside of our budgets or are we outside of it? So once again, the way you're going to perform this baselining of the legacy system is you perform system engineering. Engineer it and model it in core. You need to do the analysis. So when we look at all the different stakeholders who are going to be involved, we need to really understand what it is that they're trying to do, why they want to do it, who has the authorization to go forward and implement these particular implementations. So we have to look at something. As I don't know about you, but I think a lot of us too often jump to the solution and we don't really analyze the problem in nearly enough detail. We as system engineers bring the legacy of our history with us. We know what has worked in the past. We have ideas of what hasn't happened or where things weren't successful. And in general, we rely on our history that influences what we're trying to accomplish with the new change packages. The challenge that I offer up to you is try to control those urges. When you're discussing the objectives and the mission with your users or your stakeholders, what is it that they're really trying to do? And as you're going through that, put an emphasis on where the boundaries are. What is it that you want to be able to segregate? Are you going to segregate major pieces of the system, like a transmitter, or do you want to go down to a level such as a high-power amplifier in the Spook 9B? Those are trades that you've got to coordinate with your customer in order to establish those system boundaries. And you can model those things in Core, which I'll show you in probably about 5 minutes. Do the partitioning to make sense for your stakeholders. Again, what is it that they want to do? Can they go off and compete something at a much lower level? Do I have to compete with the supplier base at the whole radar level, or can I go down and just replace the amplifier? Well, from my experience, we found out that the traveling wave tube is a really great mechanism, but it requires an extremely high power supply. When we go to the solid state, which is the move of foot, you can have multiple pieces, multiple sub-power supplies that are summed up to get you to that maximum power that achieves the range requirements. So we found out you can't just swap out the tubes, you have to swap out the tube and the power supply. So those things are intimately related. We're going to have to do both at the same time. And the customer was very aware of it, and they recommended that when one was going to be swapped out in the design, that they would be accompanied by each other. With that in mind, that's the kind of level that NSWC Cream is interested in competing. They want to compete the power supply transmitter, and I'm sorry, the high power amplifier and the power supply that accompanies it. So that's what they want to do. And I think you have to do the same thing with your customers. What level do they want to divide the system? What makes the most sense? We may not want to do it at the IC level, but when we boil it up to higher levels, it makes much more sense. On the side of that is, how often have we made claims of an open system? Could you really grab your subsystem and put it into another design? Some people have accomplished it, but it's a real challenge because we do influence our designs based on the specific requirements that are imposed on us. And it's not that we're bad engineers, but we have design constraints, we have budgets, and then there's also company philosophies that have to be implemented. We want to use things that are inside of our control span. Look at the next slide. So when we're looking at the Spook 9B, and here's where I'm making the transition. I'm saying the Spook 9B is not just a system or a subsystem. I believe that it's a system of systems. And in the graphic, I'm showing you that there's 4 different bubbles, and each one of them I want to be able to design such that I can replace the processor. We know that the processing capability inside of the microelectronics community has been going at an incredible speed, change in pace. They're constantly adding more instructions per second, more in parallel processing. So do we want to have our system based on a 2000s processor? Do we want to be able to replace it wholesale? Other aspects on it are waveforms. As we evolve the overall radar technologies, new waveforms may be evolved to perform functionality that isn't even thought of today. But if we don't design the boundary of the processor or the antenna or the transmitter, we won't be able to swap out that entire subsystem or system inside of a system of systems because it's going to be so interrelated. Now, I had seen one example where the receiver equipment suite didn't have nearly as much equipment in it as the transmitter. There were receive functionalities that were actually inside the transmit cabinetry. So if you were going to try to replace the transmitter, you had to actually reverse engineer some of the receiver. And it wasn't that the contractor did anything wrong. They only had they had a predefined space allocation that they had to fit into, and they did. But in doing so, they didn't have a clear delineation between the receiver and the transmitter, which made it really difficult to upgrade one or the other. So when we're looking at things, what's the partitioning? And only you as a system engineer working with your customer are going to be able to come to that conclusion of what makes sense. In my paradigm for the Spook 9B, these are four of the major subsystems that we're going to work with. Yours may go down a layer or two, and there's no right or wrong answer on it. It's what makes sense based on your example. If we have a mega project, what happens is there's a lot of information, and it becomes very difficult to see with clarity where the individual design elements are. So what we're recommending, Strata is a Vitek concept on system engineering, and it's how to define what the system is going to do without influence of the performing entities or subsystems or systems. So Strata is looking at how do we go through and define what the boundaries are at the system layer that gives us the most flexibility so we don't shortchange our customers or stakeholders and give them the first solution that comes into our mind. We purview the design space, what's available, and then give the evaluation criteria and discuss it with that stakeholder community of if we do A, what are the benefits, what are the drawbacks, and then do the same thing with all the other options that are available. And we can look at the subsystems or the system of systems as boxes, whether it's a black box. I don't know what's inside of it, or maybe we look at it as a white box and we have predefined sub-capabilities that we're demanding that they're going to perform. We need to look at it from an integration perspective. If these things are going to work together, it can't be by accident. We're going to be very deliberate in defining what the interfaces are, what are the physicalities. I remember years ago there was a discussion that two subsystems that were supposed to work together. Initially it was a parallel connection. Over time they found an issue with the parallel and changed it to a serial. One of the subsystem designers came back and said, we would have been happy to make that adjustment if only someone had told us. So what you had is one subsystem required a parallel connection and another with a serial. Doesn't sound like that big a deal, but it costs a lot of money to reverse engineer out that capability that would have been very clear if we had been able to communicate the information to all the different stakeholders. Another aspect it has very little to do with engineering is the contractual boundary. If the contract officer is going to go off and procure an antenna system, they need to have the information standalone that if the winning supplier delivers their equipment, how do we know that it's been satisfactorily designed, tested, and that it performs the mission as it's prescribed to do? So what we're professing and working with Crane is that they'll be able to issue RFPs down to subsystem and even lower levels because they know what the information is. Going back to the 1980s and before that, organizations like Crane had all the system engineering capability inside of their organization, and they understood how the different systems performed, and then they would go out to contracts and then industry would provide their submissions and they could be evaluated. During the 1990s, we thought it was going to be more cost-effective to go to industry, let out an RFP, what the overall system had to do, get the best value to the government, and award those contracts. Well, using a system like the Spook 9B, there's a lot of low-level detail that we really don't understand anymore. Why decisions were made? Why is a specific configuration configured the way it is? And those things are missing based on people getting older. Now, as people retire, too often we lose their corporate wisdom and the decisions that were made when they were going through their analysis and evaluations. Going back to that methodology where Crane becomes the system engineer, they'll have that level of detail. They're actually considering not only letting the RFP based out of a model, but also requiring the bidders to submit a model back so they can evaluate what the impact of a particular design is to really establish what the value proposition is. It's not only the acquisition of a subsystem or a component, but how does it impact the rest of the system? Those things have cost as well. How easily is that upgraded? When the missions evolve, can they upgrade the missions based on what the proposal comes back to be? So we're going to define. So let's take a look at how this all is going to work together. So what I did is I have an example of the requirement spec, the SSS that Crane provided on the Spook 9B. And what I did is I just pulled an extract out of Core that shows the hierarchy of what are the requirements looking like. And this is focused on the states and modes, rather innocuous, not a really big deal. If you go back to the 80s and 90s when the system was being designed, we often had our overall system requirements at the 3.2 level. And then we defined what our subsystems were at the 3.7. Somebody purposely architected the system and said, these are the major subcomponents that we're going to worry about, and we'll call them out in 3.7. So on the right-hand side is a diagram that shows the interrelationships of the requirements and how they get a higher level of detail. Now, as we go through on this, you get a very quick and easy understanding of potential impact. If we were to select the transmit state requirement per se, 3.2.1.4, we would be able to look at everything below it and see how that requirement impacts everything below it. And we can see how those things are partitioned very quickly and easily inside of a system engineering model, something that we develop in Core. So my recommendation here is that you grab those legacy information pieces, and we talked about this, the horizontal V, the gray boxes. This is where the information comes from. My recommendation is that you don't try to design the new system right out of the chute. It's very critical to understand what the existing system did in order to put the context requirements for the new development that's coming out. What I'm showing you on this diagram is a component-based view. It's a spider diagram generated out of Core, and it shows what the Navy has called out as the major subsystems of the radar. Everything on the left-hand side of the diagram that's got a white annotation are the high-level systems. The Spook 9B is in green in the middle, and over on the right-hand side, I have an antenna unit. And inside the antenna unit, that gets decomposed into its sub-elements. So that becomes the 3.7. And if you remember back again to the 490 type specs, as you would decompose those things, that 3.7 became a new system spec or a segment spec that was further refined, derived requirements developed, subsystem partitioning, interface development, and so on. So we had our different layers of specification. What I'm going to show you in a matter of moments is that you can capture that kind of information inside of Core. And the benefit of it is, instead of having 25,000 requirements in one project, you can divide that into multiple pieces to give the engineering team a better insight. They'll have the ability to see the forest through the trees instead of being overwhelmed trying to fight through 20,000 requirements each time they're trying to find a specific concept. So then the next thing, right, so the first part is I have a model of the Spook 9B at the system level. What I'm recommending is, as an example here, we have another model or another project that contains the antenna project. At the top of the pyramid is the antenna unit, and it is broken down into sub-pieces, and some of those are divided down into lower. Now, inside of Core, for folks who are Core users, we're going to use the component concept to model the architecture elements. We're going to use the built from relationship to show relationship from one component to another, just like you would in one project, but we're going to do it between projects, and that's part of the fundamentals of how to implement it. We're going to link these projects inside of Core because we can have a single repository that has multiple or many different sub-projects that are divided up, and it can be divided by geography, company, whatever your partitioning methodology requires you to do. In addition to having the physical, you're also going to have your information and data flows traverse the projects. Well, we can have a function that's at the sub-project level tie directly into the parent, or in this case, the Spook 9B system project, so that these things are hierarchical, not only in the architecture, but also the functionality and also in the information flow. So what I'm going to show you, right on the screen, I'm showing you the depiction of the Project Explorer for two separate projects. The upper left-hand is showing you that I have a project called Spook 9B System Project. And then what I'm going to try to do is I'm going to show you that I can grab a component from another project and associate it with the master project. So when I go through and I select my built from relationship, I'll have the option of selecting a separate model. And the separate model that I'm going to be focused on is the Spook 9B antenna model, but I'm going to link directly between the projects. So let's take a second. I'm going to open up my core models. At this particular layer, I have a Project Explorer open. It's the Spook 9B projects. So I have my Spook 9B radar, and what I'm going to show you is just something rather easy. I'm going to open up a physical hierarchy, which is one of the views that are generated, and this represents the major subsystems. And I showed you that on the spider diagram previously. So what I'm going to do is I want to add in the antenna unit so that it's part of my overall Spook 9B hierarchy. I'm going to close this for a second, and I'm going to follow the built from relationship. As you see, I've highlighted a relationship from the component, and now I'm going to edit the targets. This is the secondary screen I showed you on the PowerPoint just a moment ago. The default is the project I'm working on, the system project. But what I'm going to do is I'm going to select the antenna model. And what I'm going to get inside of here is a listing of the components that are tied to that secondary project. So I can select the antenna unit, which will bring over all of its relational information, its relationships to its sub-pieces, its cross-dimensional hierarchy connections to functions, its information flows, and add that into the linkages between the models. So I have the antenna unit highlighted, I hit the add button, and now what I'm going to show you next is that that information is still readily available. Now for people who've used Core in the past, and also our Genesis product line, there's usually icons, very often anyway, there's icons in the upper left and upper right hand corners. One represents that a concept is on the screen twice. The other represents that there's a decomposition. For those of you who haven't linked projects in the past, the icon in the lower left-hand corner, the square, represents that the information you see on your screen comes from a secondary database or a linked project. The pedestal here is an idea that has a decomposition, which we can pop to as well and show that there's other decomposition. So the upper right-hand corner is the decomposition. The lower left-hand corner represents that there's another piece of information that's on a secondary project. And I say secondary, it depends on where you're working from. If I were just to go into my second project, here's the Spook 9B antenna model, the same information would be available and visible. If I hit a physical hierarchy here, you would see that the context is just the antenna unit and all its sub-pieces that are associated. So I have a linkage, but one of the benefits that I think is rather critical is that you don't get overwhelmed with data. Here's the Spook 9B and the components. You don't see all the sub-breakdowns of the antenna unit. Those are in the secondary project line. So you're able to separate your concerns and focus in on the information that's most critical to you. So I think I'm going to start running a little tight on time. I'm going to go back to the presentation mode, and we'll finish up, and then we'll ask for questions in a moment. So we went through the demo, and I want to reemphasize, we used the component, and in our example here, we used the built-from relationship to get to another component that was in a second project. And I point out, for folks who are have been using Core, we always create a context function whenever we create a component because that's where the beginning of the functionality resides. That functionality can be related from one project to another and actually should be. And for a function, it's decomposed by another function in the secondary project. So that's linking the architecture and components, the functionality in the function output at any type, and then the interfaces and information go across following the same paradigm. So tiered. you'll be able to maintain your context. So if we were going to go off and execute an RFP working with Crane, they could release an RFP specifically on the antenna unit or on the transmitter or on the receiver and have that as a standalone concept for the communities at hand to bid on and produce what their best solutions are. And the Navy would have the ability to understand, comparing multiple offerings, which is the best solution. So we have the linkages between them. We talked about the context functionality, because the antenna or transmitter also has its context and how it interrelates with the rest of the Spoot 9B, and in some situations how it interrelates with the outside world. The specifications, remember we said we could generate a system segment spec right from the models. So we can generate the overall system spec of the Spoot 9B from the parent project, but we also can generate subsegment or subsystem or segment specifications from the subordinate database, and those things are generated from the model just as well. In the old days, we called them V-specs. So summary, what I see evolving throughout the industry is that the concept of a system of systems and mission engineering, there's starting to be a commonality or an interreaction between those concepts, that it's the systems, the subsystems are going to have to be to the point where they can be replaced modularly to meet new mission requirements without a complete redesign of a system. Our recommendation in modeling is that you would have a separate project for the subsystems at the level that makes sense to you as a system engineer, but maintain all the context and all the linkages between the hierarchies of the architecture, functionality, and so on, and the requirements for that matter. These independent projects give you the insight. You're able to look at the information as it relates to your needs, consumption of those requirements, lets you support building your functional and architectural models based on what those requirements are. It provides a separation of concerns. If I'm an antenna designer, engineer, I don't necessarily care that much what the signal processor is doing. I only care about the interface. I can focus in on the areas that are important to me. Also for the program manager. The program manager now has direct insight. How do I generate my RFPs? How do I know that it's consistent? How do I know that it's complete? Well, it's based on your system models that you've built inside of Core. And you can release those out as your design package. So that was my summary. I'm a minute or two beyond what I intended to be, but we wanted to give enough time that if folks had questions, they'd have the opportunity. So at this point, I'm done with the formal presentation materials, and I'd like to open up the floor to questions. Donna?
Thank you, Fran. We do have a few questions, thanks to our participants. I encourage you to join the discussion now and submit your questions using the webinar control panel. If you do need to leave the webinar, please take a moment before you go to respond to the quick survey that will pop up on your screen. Our first question is on slide 5, and this is from Taylor. What is the reference which places segment below system?
If you would go back to, I'm going to slide back to the slide deck, so we're all on the same reference. What we see is that if the concept of a segment or a subsystem is defined inside of the example the 490 did. The difference between a segment very often was that it was an absolute major subsystem, a major concept barrier breakout. This system was the overall what I had to do, and then the segment was giving you that intermediate. If I use my Star Wars example, a segment may have been the command and control segment, or it might have been the sensor segment, or it might have been the weapons segment. When I got down to the subsystem level, I had space weapons, I had ground-based weapons. So those are just ways of logically partitioning your system, your overall architecture, so that it makes sense to you in communicating with your customers.
Okay. The next question is from Sharon. Sharon asks, I have not looked into Vitek's developments or where they stand as far as SOS modeling in the dev SML/SOA areas. Do you have data to share regarding SOS modeling efforts?
Are you saying SMS?
DEVSML/SOA.
System alternative. I'm not sure what the SOA represented. Sharon, our belief is in system engineering is that there's a unified model that contains all design ideas. And from those ideas, we generate many views. During the presentation, you saw, for instance, a requirements hierarchy or a physical construct. We have concepts of behavior diagrams. We have activity diagrams. We've made a concerted effort that our diagram generation is from the model, and it's consistent with the standards of SysML. I don't know what the question is on SOA. I apologize. I don't know if it's a system of alternatives. I apologize because I don't understand that part of the question. But we have a single design model, and everything flows from it. If we were to conduct a review with our stakeholders, we could show them the information in a context that they understand that's consistent with SysML, and then any modifications that would be made on the diagram are all automatically pushed into the model because again, the view is just a representation of the model. The overall model gets updated when the views are updated. Hopefully
Okay.
I've answered. If not,
Sharon can come back to us, either through the question tab or email. Okay, have another question. It says, once the antenna is related to the higher level project and dropped in, how does CORE help analyze impact or fit of the antenna project to the mega project?
Okay, that's a great question. Okay, so
And this is Kevin, sorry.
Oh, Kevin, what you're representing, inside of a core model, we follow an idea space that we refer to as ERA, elements, relationships, and attributes. Information exists exactly once in the model. So when we have a model that's linked to another model, the ERA is exactly the same. And the ideas that are related flow down. So if we're at the antenna level, we know what its context is, because there's actually two contexts in my purview. One is the antenna related to the external stimuli. For instance, we have the weather, so there might be moisture, and then we have our threats. But it also has a context as it relates to the transmitter system, the SIG Pro, and other elements. Because of the linkages, what we're able to do is we can do a bottom-up hierarchy trace, or we can do a top-down hierarchy trace that gives you the scope of what's potentially impacted. And I'm saying that very specifically. Core, Genesis, any other tool doesn't do the engineering. The system engineer still is the responsible agent. They're the people that have to understand what that system's doing and how it does it. What Core does it really well is gives you your very constricted space. So when I was coming up, everything was still paper-based. If a change took place in the B spec of the antenna, I had to read all the adjacent specs to try, and with a little bit of luck, I could see how those other subsystems were impacted. And then I had to trace it up to the overall system to make sure that I wasn't violating any of my system requirements. Then you also had to look down lower and what's the impact on your drawings, or if there was some other type of model that was dependent on it. So inside of Core, having a parent or a mega project associated with a sub-project like the antenna system, you're able to see what those impacts are. There's the functionality that's hierarchical and traceable. You have your physical architecture that's hierarchical and traceable. The functionality traces to the architecture and traces to the requirements as well. So I look at it as a multi-dimensional interconnectivity. And the tool will give you that insight, allow you to walk through and then analyze what's impacted by a potential change.
Kevin says that helps, thanks. Okay, so let's move on to Travis. Travis has asked, can you speak to Core's ability to run computational simulations based on the SOS model?
Sure. Integrate directly with Core. There's a simulation capability. And the simulation takes into account behavior. Functionality alone is not enough because I can say do A, do B, do C, but there's often order relationships, there are triggering and control elements, there are resources that are tied to it. Inside of core, for each and every one of the functions and then the triggering items as well as the data stores, those things interact and give you a model, an executable model that shows you the interdependencies of the functionality. We're housing, we allocate the functionality to components so we can model in if there's a separation. I think at some point, though, you're going to have to look at it. Core does a really great job of showing you the insight of how that information flows and how the functionality behaves at the system and the subsystem levels. At some point, you're probably going to have to drive a lower level model that gives you high fidelity. We would recommend you go into, like, say, a network environment. If there's a specific network challenge, that you'd have a tool that models networks really well. We would feed it, tell you what the parameters are that the network has to perform, but then adding in latencies and other effects would be at that lower level model. We would give you the behavioral. What functions take place first, for how long, what resources are consumed, what information causes it to execute, and then what are the outputs from that functionality. So that's directly related and tied to the core organic model. Any others, Donna?
Yes, if I'm not on mute, there will be others. So from Jason, do you anticipate a project database for each subsystem?
Mostly, and 90% of the time, I'm going to say yes. If your system is complex and there's a lot of detail, I think it makes most sense to have separate project models. If you have a smaller project that's comprehensible by a person, maybe two, then you're most likely going to be able to capture all the design concepts inside of a single model. For a complex system, using the Spook 9B as an example, I firmly believe there'll be no less than 4 major sub-projects that are tied to the overall parent.
Okay. And one of the last questions, if unless something comes up, is could a project model be issued as part of an RFP? This is from Amy.
Amy, that's a great question. And my work with NSWC Crane, we were just recently presenting to them how to capture the information. First, we were modeling the existing requirements, and the enlightened portion came from the customer saying, could I release a model? Could I request and ask my suppliers to model what they're going to do and get that back and evaluate it based on the model? And the answer is yes. And the group I'm working with, that's one of their goals, is to be able to have models of the subsystems and compare one suppliers to another. Because in the old days, if it was just a paper delivery, it's not always that easy to perform the analysis. If they are going to give you a model, and remember from a core model, you generate your specifications directly out of it, then you have a better opportunity to really understand what it is. There's a secondary benefit, Amy, because a lot of times the government paid for the data rights that were associated with the design. And too many times in the past, they really didn't get all those design details, and it made it rather challenging for them to support it. So moving forward, the Radar Restoration Group is very seriously looking at, can they release the overall context model and have the contractors build submodels and show how their design is superior to the competition. And we can import that directly into a core model. For Genesis, we could do the same.
Okay, we had a couple questions come in right at the end there. I think we're going to have to follow up with those offline, so you can look for information, emails coming from Fran or one of our team. So thanks, Fran. That wraps up the final Q&A for today's presentation. If you have other questions or comments, please don't hesitate to send him an email, or you can send it to me, Donna. You can see his email address on the screen, Fran, if you'll advance down to the last one. So you can see it online there. Thanks for attending today's webinar. Our next webinar will be Educating Engineers or Training Technicians by Zane Scott on April 20th. The registration link is available on our webinars page. Remember that at the conclusion of this webinar, a survey will open on your screen. Please take a moment to give us feedback on today's presentation or on what topics you'd like to see covered in future webinars. We do go over that with a fine-tooth comb. And once again, thank you for joining us and have a wonderful day.